Hey there, Math 125 fans. Going to finish this review for Chapter 2. This is my stack of books discussion when it comes to work. This is my own invention of how to think about it. Certainly not. People do these sorts of problems. I just don't know if anyone else calls it a stack of books. Watch my previous video where I actually show you me lifting a stack of books. But I want to show you where this thought process applies. We're still trying to integrate force times distance, and they're changing. It's just in these problems, we have a bunch of things that are changing. Okay, so a well is in the shape of a cylinder. So you're going to draw. Typically, I advise people to think about or draw the start and the end. Now, for a pumping problem, it's not that exciting to draw the start and the end, as I'll show you in a second. So I wouldn't necessarily do this, but I'll talk about why I'm saying this in the next example. And I'm going to draw everything. So the radius is 2. The depth is 10. The well is half full. Well, some would say it's half empty. All right, that's a stupid joke. I'm sorry. Sorry for who I am. Okay, so here we go. It's half full, half empty. And we're going to pump it all up to the top. Okay, so at the end of this problem, the water's going to be like down here at the bottom. Okay, so this is the start. This is the end. Okay. So, and we're lifting it to the top. All of that's important. Find the work required to pump all the water out of the top. And then they tell you, remember, water weighs this much. Okay, so we're in pounds, so there's no worry about this concept of having to multiply by 9.8. It's already a force. Okay, so the moment we realize it's a pumping problem or something we can think of as a stack of books, we switch to this mode. And let's label this, I don't know how I want to label it. Let's label it y equals 0 and y equals 10. Do I have to do that? Absolutely not. Okay, the next step is you're going to label a book. Meaning, pick a random place where at the start there is water. And draw it with a little bit of thickness. That is one book that we're going to lift to the top. Now, I challenge you to try to actually lift a layer of water. That's a challenge. The other question people have is like, how do you pump? Do you have a straw in there? Isn't the straw pumping from the bottom? And I always use this analogy of, when you're sitting next to your siblings and you're at Denny's and you have your soda here or lemonade or whatever, and you have a straw in there, and go to your physics instructor for a better explanation, but you got your straw in here. I don't know if you ever did this, but you put your thumb over the top and then you pick it up and put it over your sibling's head and you lift your finger and it drops on them. You might have noticed how when you put your finger over the top, the level in the straw stays the same. So actually when you sip from a straw, it only comes this far because the level in the straw is there. So even if the pump is down at the bottom, you're still only lifting from that level. Okay, that's a long explanation. There's so many other things to say. Ignore them and pretend this is a stack of books. So there's going to be one there. There's going to be another one lower. And we're going to try to find a pattern, something that's true for every one of these slices. And so in our head, we're thinking, for a given horizontal, and you have to do a horizontal slice because all of that water is lifted the same amount. So for a given horizontal slice at y, that's based off of my labeling, so I'm giving you a particular y, with thickness, I know this is a lot, but you can do it. And we'll do a few more after this, delta y. Now we're going to search for the pattern. So you have to recognize this is very different than the other type of problem we did. We're going to try to figure out how far that goes. And maybe I'll draw it over here on the empty one. So let's pretend I take this book. Now I'm boiling it down to just one question. I'm going to lift this to the top. And I would like to know the pattern for how much it weighs and how far it goes. So once you realize it's a stack of book problems, you basically just label a slice. And then you figure out how far it's lifted. How do I know it's lifted there? Because it said it was going to the top. It's important to understand these ideas in case a problem was different. Like I said, I remember we had an old exam question where they were like filling it up, in which case it was lifted this far, and that really confused people. So that's why it's important to understand the start and the end. Okay, y can be anywhere from 0 to 5. Those are the bounds. Those are the things that this could be. So that confuses people a little bit because they think that the bounds have something to do with how far you're lifted. They don't. The bounds just have to do with where the slices are, what y could be. Okay, next I want the force. In fact, I usually put the distance first here. We'll see in a second why. I should prepare, but I'm not. I'm just basing this off of 20 years of teaching this. Students always say, oh, I've been in math for so long. I've been in calculus for more than 20 years. I never get out. Okay. The distance lifted, if this is what we're calling y, and to the top is 10, this is going to be 10 minus y. Now that's going to be labeling dependent. If you labeled the top 0 and the bottom 10, then this would just be y, but the bounds would then be different. I often think about this all as one unit. And you could plug things in and see. For example, if you plug in a 0, you're going to get, it goes up 10. Water that's at height 0 goes up 10. Water that's at height 5 goes up 5. So you can use this as a little check. Okay. Now the question is, how much water is at that level? Okay, the amount of water at that level, well, how much does something like this weigh? Well, they told me that it's 62.5 pounds per cubic feet, but how many cubic feet is that? Well, I know the thickness is delta y, that's fine, but it's going to be thickness times the area. Well, the area is a circle. So let's write this all out. So it's going to be 62.5 times something times dy. And that something is the area. So students see these and they're like, okay, it's just like discs and washers. No. Yes, there's a circle there. That doesn't mean it's a disc or washer problem. All right. So this area of the circle is this. And after you've done a few of these, you realize, oh, hold on. If I label the bottom 0, it always looks like this. Yep. If it's a circular tank, it always looks like this. Yep. The only thing that changes is right here. And in this case, it's a 2, constant 2. That's it. There's the problem. All of this together is pounds. So this is the force. Okay, so there you go. So think about if you change, it's good when you finish a problem like this, or if you're working in the lab or in the quiz section, task the TA. What if we change it? What if we change the JEP to 12? What if it starts full? What if it only starts a quarter full? What's the rates? Those are the great questions to ask in the quiz section, in the lab, in lecture. And then you'll get a better sense. All right, let's look at another one. That was fun. So we're going to draw, label. These are big, scary problems, but they're an opportunity. If it wasn't for the fact that you had grades to worry about, they're a good opportunity to practice understanding how to set up an integral in a more general setting. You might recognize this question because I already did it. I did it in the last video. But in the last video, I thought of it as a leaky bucket, which I told you is unnatural for me because for most of my 20 years, I taught this a different way. And only in the last few years did I realize that no one else teaches it this way. And so I was like, oh no, but I'm not wrong. I just different. So when I always taught this, I told students, I would tell students, label the top 0, label the bottom 30, and think of it as a stack of books. It's kind of an unusual labeling, so I don't necessarily say that now. I do say multiply this by 9.8 to turn it into newtons. So the cable weighs 2 newtons per meter. And then I go, it's a stack of books. And the moment I say stack of books, I go, I'm going to label this delta x. I'm going to label this x. That's always going to be based off of what I called 0. And I'm going to ask 2 questions about that book. And that's just one of many books. There's a book here. There's a book here. Notice I drew the start and the end because I'd like to know for one of these, how far does it go? Well, it gets lifted to the top. How far does this go? Well, it gets lifted to the top. And we're basically done if we know how to read that. So at a given x, how much does it weigh? Well, the force is going to be 2 times delta x times the thickness of the book. The distance is going to be x. And we'd like to integrate from 0 to 30, x times 2 dx. Now, if you compare that to the last video, we got the exact same thing. It's just a different way of thinking about it. What I like about this is pumping is the problem that bothers students the most. And by doing the cable problem this way, we can see something that's very similar. So I kind of use the cable problem as a stepping stone to thinking about, this is why I did this when I first started teaching this course. I was like, oh, I see. If I think about, and maybe it's wrong, but I remember thinking, if I teach cables this way, then the setup will be the same for cables as well as pumping. And since pumping is the thing that bothers students the most, it's kind of nice if we can have an easier start to it. The only difference between these is that when you're doing a pumping problem, there's more going on at a given height, whereas this is just a little thickness. But to me, it made a lot of sense to realize that these are the same types of problems. So you might say that's 10 minus y and that's x, but that just depends on the labeling. If I had labeled the bottom 0, this would have been 30 minus x, and it would have looked just like that. So I like the commonality between the problems. The only difference between a pumping problem and a cable problem is that for the pumping problem, you have an area as well as thickness because you have more going on there. Okay, let's do another one. Here we go. Da-do-da-do-da-do. Sorry about sound effects. The portion of the graph y equals 3x from 0 to 1 is rotated around the y-axis. Okay, fine, let's draw that. Y equals x is rotated around the y-axis. Okay, I got it. Here's 1, but if that's 1, this is also, oh, it's 3x. I better be careful. So this is 3. Lovely. So it's a cone, if that sort of makes sense to you, this cone shape thing. Oh, it says cone. Thank you very much. The container is full of a liquid that has density 90 pounds per cubic feet. So it's denser than water, and it's full. So that's the start picture. Find the work to pump all of it over the side, basically to the top. So at the start, it's going to be full. At the end, it's going to be empty. Stack of books problem. Here you don't get to choose how to label things because it's already been chosen for you. The bottom is y equals 0 because that's what it means here. So you'd have to do this problem in terms of y. You know that the y's go from 0 to 3. And the rest of the problem becomes describing for a given y, how far does it get lifted and how much does it weigh? To me, this is the same problem as our first pumping problem. There's just a couple little adjustments we need to make. Okay, so here we go. The distance lifted, so if this is y and we're lifting up here, is 3 minus y. Notice in this case, these numbers are the same because we're lifting it all the way to the top, every single slice. If you start at the bottom and you plug into this formula. So this all together tells me here are the y values I'm plugging in and here are the distances. The rest of it is finding the force. The force is going to be 90 pounds per cubic foot times the area times dy. These flow together nicely. This is something if you can prepare, you can do well on. And then all your friends that didn't watch this video don't do as well. You can ruin the curve for everybody. And I'm fighting to get rid of that curve and make it so that we can give higher grades and just have everyone learn the stuff. Wouldn't that be nice? All right, so what do I need? That's a circle. So this is going to be pi times the radius squared. So all of this is just trying to figure out how much a slice like this weighs. The delta y is becoming this, the area of the top. And so now I'm down to one last thing, which is what is the pattern for the radius? Now in this case, it's changing. It's big up here. It's smaller here. Uh-oh. How do I label that? And this goes back to your general skills of labeling. And if you say 3x, you're in trouble. You get a ticket. That doesn't make sense. When someone gives you a function, this is what x means, and this is what 3x means. I'm giving you y. So you'd have to say what? X is equal to y over 3. So this is y over 3. That's how far that is. And we're off. Cool. That represents the force. Cool or not, you can't respond to me. So, haha, you can't slow me down. Here's another one, pumping. How does this one go? So once you start to get the feel for these, they start to hum along. Here you don't get a choice of how to label things because it's already labeled for you. X goes to 3, and if X goes to 3, that means Y is 1. I just plugged it in to figure it out. So it's the integral from 0 to 1. It's full of a container. How much work to pump it all up over the side? Okay, this is Y. Let's draw a slice right here. It's rotated, so it's exactly the same as the last problem, except that it's not a cone, but the same idea. So for a given Y, how far is it lifted? It's lifted this far. So this is going to be 1 minus Y. That tells me the distance times the force is going to be 100 pounds per cubic feet. You can see how this accelerates. This is the sort of thing that's slow the first couple times and then gets a whole lot faster. But what do I do here? I don't want Y in terms of X. I want X in terms of Y. I can do that, no problem. X squared. Oh, I'm almost running into my head. X is equal to 3 square root of Y. I know it's plus or minus, but we just want this positive length. So anyways, this is going to be pi. This is going to be 3 square root of Y squared dy, and we're off to the races. Expand, compute, done. Starting to like these better? You say, no, I don't know what you're doing. I'm asleep. I didn't make it this far. Give me a like if you're awake. One last one. This one looks scary. Oh no, it's a trough, I would call this. We're going to pump. It says it starts with 1 foot of water. This function is y equals 4x squared. This length is 3. This is the length of the trough. And we're pumping it to the top. And the liquid weighs 15 pounds per cubic feet. I remember I made a question like this once for a final, and another instructor was like, 15 pounds per cubic feet doesn't make any sense. There's no liquid that's that light. So apologies for inaccuracy here, but here we go. So what do? We label. Here you have to label this y equals 0, and you have to label this y equals 16 because they've already given you a formula, and that's what those things mean. So you're sort of stuck with that. And that's why in the first example I used that labeling, so you'd be ready for this. Okay, where are the slices? They're down here. Boom, 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 and we got it. I would like to lift that to the top. So if I give you a y and hand you a slice of water, you're going to lift it to the top. But where are the slices of water? 0 to 1. So this is going to be the integral from 0 to 1. The distance you're going to lift, because this is 16, and a given slice is at y, the distance you're going to lift is 16 minus y. So there's yet another example of what all those pieces mean. Times, and now we're going to figure out how much a slice weighs. Now this problem is different in that it's not a circular cross-section, it's a rectangular cross-section, and this is what we're calling delta y. This length is changing, let's just call it w, and this length is 3. And we know that it's 15 pounds per cubic foot times the area. The area is going to be 3 times the width times the thickness. And when everything is said and done, you realize it boils to just figuring out the width. Now that was hard for students, but compare that with our previous questions, and we'll finish it in a second. All 3 of these are the same, these pumping problems. Here, the cross-sectional area was pi times 2 squared. Here, the cross-sectional area was pi times y over 3 squared. Here, the cross-section was pi times 3 root y squared. And here the cross-section area is this. But we're going to need to find a pattern for the width. So now we have a little labeling question. I give you this function, y equals 4x squared. I hand you a y, and I want to know how far it is across here. Now the function itself won't tell you that directly, it tells you it indirectly. Because if you have a function, we've done this now a couple times, and you want to know how far it is from here to here, given a y, you just need to solve. Solve for x in terms of y. So you would say x squared is y over 4, and let's just give the positive version of it, square root of y over 2. That's what this length is. And this is the part that gets everybody. because they're not used to thinking geometrically, but that is an extremely valuable skill if you're going to stick around. So embrace this. Go back to chapter 6 in this course and make sure you can do this. If that's the square root of y over 2, then how far is it all the way across? It's not a trick question. The width all the way across here is twice that. So w is going to be twice whatever this is. You might say, why didn't we do that in the radius problems? Because we wanted the radius. This time we want to know how far it is all the way across. Okay, so this is the square root of y, and we got it, 0 to 1. I'm sure the video got too long, and I have a lot of other videos that do this, but I just want to finally put this topic to bed after 20 years. We got it. So I've given you a process to attack all these problems, and I hope that helps. Draw the start and the end. Identify the force. So kind of hold this next to each one of these. We had to figure out the force. The distance in all of these was 10 minus y or x. The only time this is any different is in that robot problem. And I think I've already posted about that too, but that's the challenge question. If you don't know what I'm talking about, that's a question in our homework, and I'm sure I'll be talking about that in some future video when I teach Math 125 again. Alrighty. Now go ace those questions. All right.